Hello everyone, today I am here at ISSCC 2012 to present demo for our paper 3.6, a 280 mV to 1.2 volt wide operating range IA-32 processor in 32 nanometer CMOS. The key objective of this NTV processor is to showcase energy benefit of near threshold computing on IA-32 core, and also showing the wide dynamic range energy performance trade-off for the IA-32 core. To achieve reliable ultra-low voltage operations, we did variation-aware library pruning for the combinational cells. Only 40% of the library combinational cells are used in this design. We also optimized the flip-flops. We use the clock CMOS flip-flop topology, where we have contention-free write and also the better retention VCC min. We optimize the flip-flop for 500 mV retention VCC min limit. All the L1 caches what we have in this course are designed using the 10T single-ended transmission gate latch topology with interruptible keeper. We have sized the bit cell to achieve 550 mV of the retention VCC min for the memory cell, and also we use the strike keeper in the read bit line to achieve reliable read operation at ultra low voltage. To achieve the wide operating range operations, we use the multi-corner verification and the optimizations. We optimize the design at three different points: 0.5 volt, 0.75 volt and 1.05 volt. Using this multi-point verification approach, we converge all the min and max timing across wide operating range. As shown in this poster, this core is designed in 32 nanometer. This core contains 6 million transistors and occupies 2 millimeter area. We have the different voltage plane for the logic and for the memory because they have the different VCC min requirement. Along with core, this die also contains the IO area and the PLL and the JTAG part. This core can operate wide operating range starting from 280 mV to 1.2 volt. At 280 mV, the core performance is 3 MHz and then scale up to the 915 MHz at 1.2 volt. The power is scaled from 2 mV to 737 mV, that goes from 280 mV to 1.2 volt. The below curve shows the energy graph for this core. The energy is scaled down from 1.2 volt to 450 mV, where we achieve the minimum energy point. At this point, the energy is around 170 picojoule per cycle, and this energy is 4.7x less than the nominal point energy. This pie diagram shows the power breakdown at three different operating points. At high voltage, when the logic and memory both operate at high voltage 1.2 volt, the biggest power contributors comes from the logic dynamic power, which is around 81%. This power reduced to 4% at VCC min point. The leakage power start increasing from the VCC off point. At this point, the leakage power is around 42%. At sub-threshold region, where the memory still work at high voltage, the leakage power from the memory take the maximum contributions. The leakage power from the memory is at this point is 62%. This is the package silicon for the NTV processor. Here the silicon is packaged on 951 flip chip BGA package. Since this package cannot be connected to the socket 7 old Pentium motherboards, so we connected this to the interposer, which is customly designed. This package silicon with the interposer can connect to the old socket 7 motherboard for the post-silicon testing. For demo setting details, I will refer my colleague Suruth.
Thanks Shailendra. So what we have here is this wide operating range Pentium processor, which is retrofitted into this old Pentium motherboard. So we have a custom interposer for that, and power supplies for the interfaces and IO circuitries are fed from these wires coming from the power supplies. Now we are powering this processor from this small poster size solar cell, and we can see the processor booting Windows operating system and running a couple of workloads there. So the CPU usage is currently about 85 to 90%, and power drawn from the cell is approximately 15 to 20 milliwatts in this case. So this tells us the amount of power savings or energy reduction which we can achieve by enabling the processor to operate in the near threshold voltage range.